Hello friends, Agrawal is Assistant Professor in Civil Department, Sandipani Technical Campus, and today's topic is the examples on the conjugate beam method. Now the learning outcomes after watching this video, student will be able to understand the concept of conjugate beam method, and also student will be able to calculate the slope and deflection by conjugate beam method. Now the theorems, the first theorem is the shear force at any point on the conjugate beam is equal, that is in sine. Next theorem is the moment at any point on the conjugate beam is equal in sign and value to the deflection at corresponding point on the real beam. Now the steps in the conjugate beam method. First is to determine the bending moment diagram for real beam. Then next, apply this M by EI load on the conjugate beam. Next is to determine the reactions of conjugate beam. Then next one is to determine shear force in the conjugate beam where the slope is required in a real beam. And the last one is to determine bending moment in a conjugate beam where the deflection required in the real beam. Now some sign conventions here. The sagging bending moment for real beam use the positive bending moment M by EI diagram, and hogging bending moment for real beam use the negative M by EI diagram. Then next one is positive M by EI diagram means upward loading on the conjugate beam, and negative M by EI diagram means the downward loading for the conjugate beam. Then next one is the positive shear for conjugate beam means anti-clockwise rotation of a tangent drawn to elastic curve with respect to original position at corresponding point in a real beam and vice versa. And the last one is the positive bending moment for conjugate beam means the upward deflection of a corresponding point in a real beam and vice versa. So now we take here the example. Now suppose this is a fixed beam, and here is a one pin inserted. Then next is the key support. It is subjected to and this span is a 1.2. Then again this span is a 1.2, and this is a 1.5, and here one moment clockwise acting at this support, and that is a Newton meter is A. Then slope and deflection at here. Now here, suppose here, if you draw the deflected shape of this, the beam is like this, suppose. This is the deflected shape now. So we can see that here. Now tangent. So this angle we called as theta b right, and if we draw the tangent at here, and this is the angle, so this theta is called as theta B left. Now here we are separating this beam here. We apply only the here the moment and bending moment diagram. Now we know here, so draw here the three body diagram for this beam. Now suppose here, if you assume this direction is vertical, that is the RC. So here is the downward reaction, and the same, that is the this direction. So 1, and this is the RB2. So now this becomes the prop cantilever. So first we solve this. So we are taking the bending moment or moment at the, so we can say that sigma MB at here. Sigma. So this is clockwise. So this is a now this is the anti-clockwise, that is why is minus that RC into 1.5. The distance is a 1. So here is equal to 0. So RC 3 by the 1.5. So that is the kilometer. So this automatically becomes this is downward 2 kilonewton. Automatically this becomes the upward. Now we can find it this fixed moment. So we can take here sigma MA is equal to sigma MA here. Now suppose we assume this direction is the clockwise. If the answer is positive, so our assumption is the correct. This is the MA. So clockwise is the positive here. Anti-clockwise, that is why is minus 2 into the 2.4 is equal to 0, because this distance is the 2.4, 1.2 and 1.2. So this MA is equal to the 4.8 kilometers. So this answer is clockwise is correct. So now BMD for this portion. So we are taking here first only this couple at the support. So we draw here the BMD. Now we know here this point where the hinge, where bending moment is the 0. Now this support, this 3 kN is create the sagging bending moment. This hogging bending moment, sorry. This create the hogging bending moment because this try to lift this upward. So we can say that this is the 3 kN the downward, because it is negative. Now we join this line and this is the negative part. Now again here at this support A, we know this is create pressing downward to this beam. So this is sagging bending moment. and that is a 4.8 kilonewton meter. So here is a 4.8. Then join this line. So this is a positive. Now divide by this EI, so that becomes the M by EI diagram, and this is the again divided by the EI. So we know if the now this we apply on the conjugate beam, so that will be the latter part. Now again next part. So this is the M by EI diagram for this the movement part only. The next is the point load. So now we draw here the point load 3-point diagram for this point load. This is a hinge and here is a hinge. Eight kilonewton. This is a 1.2 and this is a 1.2. Now this is a reaction because this is a downward reaction load. So with the upward reaction, this is RB1 suppose. So it is upward. So here is the downward force. So it is downward. This is the upward force. This is the RC. But from this, because this is a this part, this A to this B, this is a nothing but the prop cantilever. So this we cannot solve directly. First we find the reaction this RB2. This RB2. So if we observe this beam B to C, this B to C, so we can say that there is a no load here on this beam. That is why this reaction is 0 and also this reaction is the 0. So automatically this RB1 is the 0. So we can say that this RB1, this also the 0. Now once the RB1, find this MA. This is the clockwise, so we assume this is anti-clockwise here. This is MA. So if you take here the sigma MA is equal to 0, this is a minus MA, and here is a this is the, but here this we are taking moment at A, so this becomes the 0. The next force is a this is a clockwise, so plus 8 into 1.2 is equal to 0 because this RB is the 0. So MA is equal to the 9.6 kilonewton meter. So again this is answer is positive, what assumed direction anti-clockwise is correct. Now next part is to draw the BMD for this part. So now here we draw the BMD. Now for this portion is a no bending moment again from this, suppose the D point. So there is also the no bending moment. So bending moment is only at the this A, and this is a 8 into 1.2. So this creates the hogging bending moment. So that is the minus negative, and that is the 9.6. Now here is divided by EI. So this becomes the M by EI diagram. This is the M by EI diagram. This is A and this is the B, this is C, and now this is the D. So now this again this is BMD, M by EI, and this BMD now we apply in the conjugate beam here. So here, so this is a, suppose we draw it separately. and this is the 9.6 divided by AI. Now we know this part is positive, it means this loading is in upward direction. So this is the addition of these two beams. Again we know this is the negative, so this is the, as per sign convention, is a downward load. So this is the conjugate beam. Again this is negative, so this is a downward load. This is A, this point is B, C, and this point is the D. Now again here, as per the conjugate beam, this is the make the free end, because we are making fixed end as a free end. So that is why this is a free end, and here is apply the one support. Where the hinge, we have to apply one the support. So here apply the support, and hinge is a hinge support in both the cases, real beam in the conjugate beam. Now next part is to find the reactions for this beam also and for this beam also. Now first we find this reaction RC. Suppose. So we are taking the sigma MB is equal to 0. So for this beam. Now, so take the, this is the loading on the beam. So this is the clockwise, that is by plus, that is 1/2, base is 2.4, is 4.8 divided by EI. Then multiplied by the distance. This is the distance x bar, suppose. This is 2/3 of this 2.4. 2/3 of this 2.4. Then again here, this also rotate in the clockwise way, this load. So plus 1/2, base is 1.5 and height is 3 by EI. Again this is x bar, the 2/3 of this 1.5. So 2/3 of the 1.5. Now here reactions. This RC, suppose. It's RC. So this is anti-clockwise, that is by minus 1.5 into the RC is equal to the 0. So this RC is equal to 7.644 divided by EI. And this value is positive, it is what we assume direction vertical is the correct. So we got here RC is equal to 7.644. Now next part is the Now next we find here the reaction at this beam RC. Now here we again take the sigma MB equal to 0. Sigma MB is equal to 0 at here. Now this is anti-clockwise, so we can say that this may be the clockwise, so we are assuming this direction is downward, this RC. So this is anti-clockwise minus the 1/2 base is 1.2, this distance is 1.2 into the height 9.6. Now this is x bar here, so this is 1.2 again, so 1.2 plus 2/3 of this 1.2, so multiply here 1.2 plus the 2/3 of 1.2, then this is a clockwise, so plus 1.5 into the RC is equal to 0. So here we got the answer, RC is equal to 7.68 divided by EI. So this answer is positive. It means what we assume direction is the downward is the correct. So we got here the 7.68 divided by EI. Now important is here now form. So here from this theta is from the right side, theta b from the right side, and this is theta b from the left side. So if you want to find the theta b from the right side, we have to find the shear force at b from the right side. So we can say that here from this original figure, theta b from right side, that is equal to the shear force at B from the right side, from the RHS. So at this B is shear force from RHS, and also at this B shear force from the right side. So now we can say that here we know from the right side sign convention is from left side upward force is positive and left side downward force is the negative, and from right side the downward force is the positive and the upward force is the negative. So now we can say that here this reaction here RC 7.644 divided by EI. So this reaction is upward. So from right side that upward reaction is negative, so that is minus. So we can say theta b from the right side, that is equal to minus 7.644 divided by the EI. Then this reaction is downward, so from right side downwards is plus, so plus 7.68 divided by EI. Then next is this load. So this is downward load, that is a positive. So plus this load is the area of that triangle. So 1/2 base into the height is divided by the EI. So this is the theta b from the right side. So theta b from the right, so that is equal to here 2.28 divided by EI. Now this answer is positive, shear force is positive, it means the anti-clockwise angle. this angle is the anti-clockwise. It means if you measure here, so in this way, this is the anti-clockwise. So theta b right side, that is the anti-clockwise and that is the positive. Then next part is the theta b from the left side. Next part is theta b from the left side. So here we can say that theta b left is equal to the shear force at B from left side, from the LHS. So we can say that here from the left side is these two forces. This one triangle and this is the another triangle. So we can say that this triangle is upward. So from left side, this upward force is the positive, and this triangle is downward. So from left side, downward force is the negative. So we take here the area of the triangle. So theta b left is equal to here 1/2 base into the height divided by the EI here. It's a positive, and negative is the small triangle, that is 1/2. Base is 1.2 and height is 9.6 divided by EI. So this answer is the 0. This answer is the 0. So theta b from left side is the 0. And theta b from the right side is 2.28 divided by the EI. And this is the P1. The next and last part, that is the deflection at the B. So deflection at B is equal to the bending moment at B. So we can say that delta B is equal to the bending moment at B. Now here we can take it from left side or make it from the right side. So we are taking it from the left side. So bending moment at this B is from the left side also, and bending moment is from the left side also. For this B, we know this area of triangle. Now from the left side, this is positive. So this is a 1/2 base into height into 2/3 of this, the total distance, which is a 2.4. And this moment is a minus because it creates the hopping bending moment. So again, area of the triangle into the centroidal distance. So that is equal to here 1/2. This base is, we know, is 2.4 into 4.8 divided by EI into 2/3 of the 2.4. This is a plus, and next one is a minus. There is 1/2 1.2 into 9.6 divided by EI. This is the area of triangle, and distance is, we know, is 1.2 plus the 2/3 of the 1.2. You can check here, 1.2 plus the 2/3 of this 1.2. So this delta B becomes this is 9.6 216 divided by EI, and this becomes minus 11.52 divided by EI. So final answer is the delta B is equal to minus 2.304 divided by EI, kilonewton meter cube. Now this negative, as per our sign convention, this negative means the deflection is ground. So we can say that delta B is equal to 2.304 divided by EI kilonewton meter cube, and this direction is the down. So this is the deflection at the, in this way we have calculated the slope and deflection at the way. Thank you.